So this is the book that I've written on time series forecasting, and this is the talk is going to be in and around. I mean, we're not going to be talking about everything in the book, but we'll try to touch up on major pieces so that we get the gist of it. So yeah, so my name is Manu Joseph. I'm right now working with Walmart as a staff data scientist. I have about 10 years of experience, 10 plus of years of experience, worked in different things. A large part of it is actually in time series forecasting, which where I've kind of developed forecasting systems for a lot of companies. And this book is basically like a crystallization of that experience. So I'm active on LinkedIn. I'm also available on Twitter, although more of a radar than more of a radar than anything. And that's my GitHub handle. So if you want to get in touch with me, you can do it through any of these channels. All right. So yeah. So this is the book in question. I'll quickly go over the table of contents so that you get an idea about what the book has, and then we'll get on to the talk, right? So yeah, we start off the book by talking about introducing time series and how do we work with time series, how do we visualize time series, etc. Then we spend a particular chapter called setting strong baseline forecast, where we look at all our classical models like our IMRs, exponential smoothings, and all the related family. And then quickly we move on to like how do we use time series as a regression, how do we do feature engineering, how do we do target transformations, how do we do ensembling and stacking, etc., etc. And then we talk about global forecasting models, which I'll be talking a little bit in detail in this talk. Then we also look at the deep learning side of it. So the book does not take any assumption that you already know. So it kind of takes starts from a very basic kind of what is deep learning and what are the different building blocks and how do we commonly model for time series. And then we also look at how do we make global deep learning models better. And to close off the book, we really look into like how do we do multi-step forecasting, which is the moment you move away from classical kind of a setup. Multi-step forecasting is an exercise. You'll have to think about it. It won't come for free. And then we also talk about how do we evaluate forecasts, which is very important, and how do we use proper validation strategies to make sure that your model isn't overfitting. So all of those things are in the last part of the book. So to summarize, I think it's basically like an end-to-end book which kind of enables you to start building systems for the industry right away. And that's kind of like the I don't know, the USP of the book assessment. All right. So with that, let's look at what we have on the agenda today. So similar to the book, the structure is pretty much the same. We spend about 2 slides to like as an introduction to time series. And then we jump on to how do we do machine learning and deep learning for time series, and then we talk a lot about global forecasting models, etc. And we'll end the whole thing with a Q&A session. All right. All right. So time series forecasting. Right? So we've been like mankind has been doing time series forecasting or forecasting since the like very olden days. Right? Shamans and oracles used to do that in the past, but nowadays data analysts, data scientists have taken up the mantle, and this is very important to mankind even back then, even now, because forecasting is something that is very essential for planning. For anything that you need to plan, you need to know what's happening in the future so that you can plan accordingly, because of which it's been a big topic right from the beginning. And also time series forecasting is not a new topic by no means. It's been there for decades. Statisticians and econometricians have been doing very good work in this area. So no discussion about time series forecasting can go without mentioning a few of these very robust methods. Most of these methods have been developed like 50, 60 years ago, and we're still using them, and it shows how robust these methods are. Like I'm not going to go into detail in any of this because I'm assuming all of the audience are aware of this, especially since this is the time series group. So very basic models like naive and moving average are also very tough benchmarks to make to beat in many cases. So if a model is not doing better than a naive or a moving average forecast, then like there's no point in let's just use the naive forecast. That will be better off. You have a very rich family of methods in exponential smoothing. You have single, double, triple, and it's also a state space model. So it's have a lot of combinations in there. IRIMA, as you all know, it's a very battle tested and with strong statistical foundations. It's a method that has been used very popularly. And there are also a few methods like a fast Fourier transform or a singular spectrum analysis, which are more niche and more typically suited for seasonal series in this case, etc. Right. So the reason I start the talk with these methods is that these methods form a very strong baseline for us because I'm somebody who believes that setting yourself a strong baseline is essential to in getting a good model out, right? So like if you're able to beat these models, only then it makes sense for you to put all the effort into more complex models. So any start of any project so will pick one of these methods or few of these methods, have a strong baseline, and then go into the real meat of the work. All right. So before we get into all of that, I have a say a question of sorts because this is one concept or one terminology which is not standard across different literature, blogs, etc. So yeah. So let's say that we have a time series. Let's say we have one target, and the whole point of forecasting is basically we are trying to learn a function which takes in that history and tries to predict the future, right? And this particular thing, it's called like I'm going to answer this myself. This is a univariate forecasting, right? We are all aware of that. All right. So then suppose you also have a few covariates, right? You have a target and a few other time series which makes it easier or which helps us forecast this. We're still concerned about the target itself. We're only forecasting the target, right? What do we call this? Right? Is it a univariate? Is it a multivariate? Or is it something else? Anybody from the audience?
Do you predict also covariates?
I'm sorry?
So it is univariate still.
Correct. Yeah, this is univariate still. Yes. Because this is one thing that I've seen in a lot of literature, or basically not formal literature, like blogs and other discussions where people kind of call this as a multivariate time series and then have discussions around it. So multivariate time series is this, right? You have three targets and you're trying to forecast all three into the future. And this is a much difficult task than the others. And there's another class of models, which is something called global forecasting models, which comes in somewhere between univariate and multivariate. It's a slightly in the gray area. We'll talk about it in the later slides. All right. So now let's take a step back and talk about machine learning for a while. I'll just take one slide to kind of put machine learning into a context and kind of explain what it is. So suppose that we have, right? Yeah. Suppose we have, we're interested in something, right? Let's say we have a target. We are interested in something. Let's say in this case, let's say whether or not a customer is going to churn. Right? It's a very common use case for this. So we are interested in that, and we have collected some details about that that customer. We have some features, right? These are the independent variables, right? And then we know that there is some ideal function, right, which would just take these features and give you the target, right? But the problem here is that this ideal function is that something that we don't know. Typically in machine learning, whenever machine learning comes in, it's an unknown target function, because if you know the target function, then you can just put that into a just code that up and then you're done with it. You don't need machine learning. But then yeah, so this is where machine learning steps in and says that, okay, we don't know what G is, but we're able to we're able to have some kind of a function, let's say a function h, which takes in this features, and there are a few parameters, let's say something to tweak the function, and then I'm able to predict a target, right? So now this is a framework that machine learning comes to brings to table. But in this case, what we really need to do, or what we really want, is that the approximation h to be as close to G as possible, right? So in the supervised setting, this is where a data set comes in, where we have examples of examples of X and Y, right? You have some features about a customer and information whether he has churned or not in the past. And we have some large data set, let's assume. So now we're using this data set and something called a loss function, which measures the deviation between Y and Y hat. And we're training the whole model. And by training the model, what we're doing is we're changing the model parameters, sometimes the model class as well, but then the model parameters, so that Y hat kind of approximates Y as close as possible. And once that happens, once the loss function makes sure that Y and Y hat is very, very aligned, then the H that we have got now is going to be a very good approximation of G, right? So all of supervised machine learning, deep learning, everything boils down to this, right? This is what we're doing. We're learning a function to approximate some unknown function. So now, with this in mind, let's look at two paradigms of predictions. Right? On one side, we have time series forecasting, which basically says that I have a sequence of values which is taken in time, recorded in time. We have t time steps, and then now we want to forecast what is t plus 1, what is t plus 2, what is t plus 3, etc. On the other hand, we have regression, which is basically machine learning for continuous variables. We have like a data set of examples. We have x's and a corresponding y, right? On the face of it, this looks very different. But the question is, can we make or convert time series forecasting into a regression? But you may ask, why do we want to do this? Because so in the last decade or so, machine learning and deep learning as a field has grown exponentially. A lot of new developments have happened in the space. So it would be really good if we can leverage those for forecasting time series as well. Right? This is the thought process behind we're trying to do this kind of a thing. So suppose you have again a time series which goes from 1 to t. To convert this into regression form or a machine learning form, there are two major classes of methods or ways of doing this. One is called time delay embedding. It's also called sliding window, because true to its name, what it does is we define a window. Let's say that in this case we have a window of 3. We have a window of 3, and in the 3 window, we say that we take those 3 data points, 1, 2, and 3, and we say that the target is 4. And we move the window 1 to the right. We have 2, 3, 4, and we take the target as 5. And then we keep moving this window over this till the end. So at the end of it, you will have an X and a Y matrices, where you can see that the first column would be t minus 3, and second column would be t minus 2, and the third column would be t minus 1, and then we're going to predict t. Right? So it's very similar to what we do, a part of what we do in ARIMA. We're basically using the lagged variables to predict the future. Right? So this is one way of doing it. So in this way, we have actually used the information which is there in the yellow bubbles, which is the actual value. Right? But there is one more source of information in here which we can use, which is the time itself. Right? When you and me think about time, we think about time in hours, in minutes, days, years, right? But a machine or a computer doesn't really do that. So we have to enable that. So when we have to kind of extract such information, such hierarchical temporal information, and we can provide that as an additional information to the model. Is something called temporal embedding. So let's say that 1 and 2 is month 1, 3 and 4 is month 2, and this is quarter 1. I know 2 months are not a quarter, but just for explanatory purposes. And like this, right? So now you can change this or convert this into a regression kind of a data frame by saying that my first feature is going to be a month, and second feature is going to be a quarter. So I can represent 2 with M1 and Q1, let's say 5 with M3 and Q2, and so on. So in practice, we do much more than this and a combination of this as well to get good, really good models. But conceptually, these are two different sources of information that we extract information from. Yeah. All right. So now, before going into the next section, I'll just quickly talk about a data set which is used in the book all throughout. So in the book, we basically take this data set from the beginning. We develop the baselines. We develop the machine learning and deep learning models, everything on this one single data set. So we're not going to be doing anything hands-on in this session, but still just to get a context on some of the results, some of the things that I'm talking about in the rest of the session, you can probably quickly take a look at it. So it is basically a energy consumption data set, energy data set. It has 5,500 odd households in London, which has like the recordings of the energy consumption. It's a half-minute interval data. And it also has some other information that you have something called Aecon groups, and you have something called the weather and the UK bank day, holiday data. Some other information to help the whole thing. And then yeah, this GitHub repository is like the companion repository of the book. So all the scripts and the function that we'll be talking about in this talk, you can find everything in this thing, and it's free. Like it's an open repository. All right. So now let's talk about machine learning for time series. Right? How do we use machine learning? So like we said before, the first and foremost thing is lag features. Right? We just talked about it earlier. The concept is very simple. You take the t-1, t-2, t-3, and t-4 as features. Right? If you define 3 lags, so the first t-1 is called the lag 1, lag 2, t-2, and t-3 is the lag 3. And in pandas in Python, it's very simple. Just to do like you can just select the column that you want to have, and then just do shift 1. Right? That will shift and give you the lag ones. But when we do this for a large data set, like you have these 5,500 odd, right? You have to do this shift for each of those households or time series separately. And you can have you can create a lot of lags as well. So for all of that, we've just defined a method called add lags. It kind of does the whole thing in a very efficient manner. So all you need to do is just give the lags that you want to create. Like in this case, I'm creating 1 to 5, then like some different lags I'm creating, and just I'm giving that lags as a list of lags to the model or to the method, and just specify which is my column that I want to create the lags, and which is the unique ID for each time series. Right? So once you do this, all the lags will be created, will be added to this full DF, and you'll get it back. And so adding lag features is very simple, and it's a bare minimum that you need to do. But there is one challenge with adding lag features, is that when we are adding more and more lags, right? If you want to cover a large memory history, that means that for each lag that you're adding another feature. And pretty soon, the number of features would become pretty large, and we'll go into something called recursive dimensionality, where where getting a good model out or learning a good model becomes very, very difficult. So as an alternative, or as an alternative to adding more and more lags, we have something called rolling window features, right? What we do is we define a window, let's say a window of 3 or a 4, right? Just like we did with lags. But instead of taking those 3 or 4 as features, we're going to use some kind of an aggregation function, whether it's a mean, standard deviation, anything that you want to. I mean, any aggregation function, basically the end would be a single result. And we are going to extract such single aggregated results to capture the information in that window. So we can define multiple rolling windows depending on the domain and basically what you think would be relevant. So in this case, I just added 3, 6, 12, and 48. Again, in barebone pandas, it's very simple. You can just do a dot rolling 3 and just take a mean for a window of 3. Dot shift 1. Okay, we do this dot shift 1 or dot shift to make sure that there is no data leak, right? For example, if we're not doing this data leak, shift 1, that means that the window would start from T. And that means that we are actually taking T as a feature to predict T. And that's not something that you want to do. And that's why we have the shift always. Yeah, so this is how you do it for a single time series. And for multiple time series, is like before, we have a method in the repository called add rolling features. You can just give the number of the number of windows that you want to have as a rolling function, the different functions that you need to give. So these are all strings, like these are all standard pandas functions, and you can even give like a custom function as well in this, and it will still work. Right, and then this is how rolling windows, and this kind of resolves our desire to include more memory into the model at not having the cost of having additional features as well. And another type of feature that we typically, especially for seasonal products, right, seasonality heavy time series, is something called a seasonal rolling window. So one way of doing this or capturing this is basically just including the corresponding lag, right? So for example, if I expect the seasonality to be an yearly one, I can just include the same time last year value as a lag, and that should work fine, right? But another way of doing it, or basically a slightly better way of doing it in some conditions, is take a rolling window on seasonal item, right? So instead of just taking my last year, I take an average or a standard deviation of the last 3 years same time, so that this number that we get is slightly more robust than just taking the last year. But again, this has a slight caveat, which is basically if your time series is having strong trends, upward or downward, then this might not be the best strategy. Right? Like taking the most latest lag would be the best strategy there. But if there's no trend, or if you've already pre-processed the trend out of the series, you can probably use this as a better alternative. And for this as well, there is a method called add seasonal rolling features, which is again an efficient method using NumPy, etc. in the backend, so that it runs fast for very large data sets. All right, so now we have one more type of feature, which is called the exponentially weighted moving averages. So the concept is pretty simple. This is basically like an infinite window, like moving like an average, right? But for each window, we apply an exponentially decaying weight. Okay? And how much this decay happens is actually controllable by a parameter. It's popularly called alpha. It's also the same alpha that you see in exponential smoothing methods. So you can create such weights and use those weights to average out the whole thing. It's similar to exponential smoothing in one way. But the plus point or the positive about this is that um, yeah. So that is also, if you notice this, right, this might be too small, but if you notice this, right, you can see that at alpha 0.3, this is decaying pretty fast, and at about 5 or 6, it approaches 0. When you're getting it up to 0.5, it approaches 0 much faster, right? So by controlling this alpha, you're actually getting to include different windows, like in one way. So instead of tuning and figuring out what is the right window to include from the rolling window side, you can also use this and kind of tune these parameters, which is much more easier to tune. You can just change the parameters and then get different window rolling features in there. So instead of alpha, there is another thing called span, which are equivalent. So span basically lets you think of it in a more intuitive way. So span basically tells it that I want to look at the last 48 into 60 window or 48 window, right? So the weights and the alpha will be adjusted accordingly. So again, there is a method which is already defined. We can basically just define these are the different spans that I want, or you can even define the alphas that you want, and mention that this is the column that I want to do the moving average on, and this is the unique ID over which I need to calculate this over, right? So all of these different features help us capture the temporal aspect of time series, because machine learning it has nothing to do with time, right? It has no concept of time at all, right? Um, Sorry, am I still audible?
Yeah, everything's fine.
Yes, right? All right, cool.
Yeah.
No, I heard something in my headset and I thought it went off. All right, let's get back. All right, so like I said, machine learning has nothing to do with time. Right? It is no time concept at all, as opposed to the other models that we talked about earlier, right? Exponential smoothing, IRIMA, etc. They all have time kind of embedded within the model or the modeling formulation, right? But machine learning is more general. So to get good successful models or machine learning models to work, it really depends on how well they're able to capture the temporal aspect of time series in different features. Right? So all the features that we talked about are ways of capturing the temporal dimension. And then we also have the temporal embedding features, which is basically all the calendar features that you have, right? You can have month, quarter, day of the hour, etc. Like depending on the periodicity of your series, you can define like the relevant ones. Right? For example, if your data set or if your time series is a weekly time series, there is no point in defining the hour or the day of the year, etc., day of the week, etc., because it's a weekly time series. But then, yeah, you can just use your common sense to understand what features would make sense, and you can extract such features from the time that you have and use that there. And you can even also create something called time elapsed, which is basically like a simple linearly increasing kind of column or feature, just a proxy for passage of time. All these you can just add by giving this using this method. It's called add temporal features. You can give the column where the time is. You can give the frequency of the data. Like this is a 30-minute data, so I give 30-minute, and all the rest is taken care by the method. Like it will automatically take up whatever is relevant and add it to the whole thing, the full DF, and return it. So so we talked about including the temporal features, right? Features like month, for example. But there is another way of doing it, and in some cases it's a better way of doing it, which is basically Fourier terms, right? So typically when you encode or include let's say the month example, right? Let's say the month variable. You either encode it as an ordinal number, like 1, 2, 3 to 12, or you do it as a categorical value. Right? When you're doing it as an ordinal value, it makes sense from 1 to 12, but then it has the step function that it goes to 12 and it goes right back to 0, I mean 1, and then it goes back to 12 and it goes back to 0, etc. So this representation of time is not complete, right? You don't know that after 12, 1 comes in a continuous spectrum. That information is not really there. And on the other hand, if you're displaying it, I mean, encoding it as a categorical features, we don't really, so we are actually learning each of these values, like Jan, Feb, March, etc., as totally independent items, right? We're not considering the relationship between them. So for some models, like the decision tree based models, the step function is not a big problem because they do have the capability of kind of making hard partitions in the data. But other models like probably deep learning or SVMs or other models doesn't really work that well with step functions. And for such cases, and in some cases for decision trees as well, you can include them as Fourier terms. So Fourier terms, we all know that there is this theorem that says that any signal can be represented by its corresponding Fourier terms given enough terms are there, right? So it's just basically different frequencies of data. So this is the formula that is the Fourier expansion formula. So we can basically use these terms which are in highlighted as features and kind of learn the coefficients, right? AN and BN coefficients. So we can add this kind of representation into the model so that the model has a better representation of time and the cyclical nature of time, and make the model better, right? Again, there's a method that is already implemented. You can just give the data frame, which all columns you want to encode it in the Fourier way, and also the maximum value of these columns, right? Because you need something to divide this by the p, so that the cycle aligns with the expected seasonality. So month is basically 12, hour is 24, and minute is 60, etc. And then we can define the number of Fourier terms that we need to add. So if you keep increasing this number, the representation gets more and more complex. So basically, it's a hyperparameter. You need to understand or find out the sweet spot where you get best performance. It's basically like a hyperparameter that you do, right? So now with all of these features, you can basically train. So now you have a data set which is in the machine learning form. You can use any model, any machine learning model which supports regression as a model to train these models. Right, so that's what I've done in the book as well. I've just looped over all these 5,500 time series, used the standard ML workflow to train these models, right? Sorry, and the results are this, right? So you can see that the naive and seasonal naive is around 0.86 and 0.122. And all the machine learning models, even a simple regression, is doing better than the naive forecasts. And the best is basically Light GBM, which is one of the gradient boosting models, XGBoost kind of models. And fun fact is that in almost all the projects that we worked on, invariably we come up to one of these models for deployment. But yeah, so this is when we are making it like a one-by-one model. We loop over everything, you train a model, and we predict it. And these are all single step ahead, right? One step ahead models. So we're not going to be talking about multi-step models in this session. But yeah, so it's once you have a single step model, there are ways to make it into multi-step. Basically, just need to write a little bit of code. All right, so now this is all about machine learning right now. And right now, let's move on to deep learning for time series, right? So, yeah, so I'm not going to go into a lot of detail on the deep learning side because there are a few prerequisites which need to be there, at least in a session like this, where I don't have the luxury to take all of you from the beginning of the from the basics, right? But then what I am planning to do is to put like help you think about these deep learning models in a particular way. Right? So deep learning models is this again falls into the same machine learning fundamental that slide that we saw earlier, right? Deep learning is basically machine learning itself, but it has some peculiarities to it. But at the end of it, we are still learning a function by using some method. All right. So most of our of the time series models, most of them fall into this encoder decoder architecture. I'll explain what that is. So as we seen earlier, any time series model, we are essentially learning a function h which takes in the history t minus 1 to t minus n and predicts t. Right? And now from mathematics, from high school mathematics, we know that any function can be split into two. So suppose we have a function called h right now, but it's not predicting yt, but it is predicting zt, right? Let's assume. And then there is another function g, which takes in zt and gives you your y, or the thing that you're predicting, right? And this is pretty much what an encoder-decoder model is, right? So the encoder model, so let's say that you have an input, right? X is your input. In this case, this yt minus 1 to yt minus n, this is your x. So this is in some space, right? Some vector space. So the encoder, all it does is it takes the input space as an input and it projects it to a latent space. Let's say it's a z vector, it's a latent vector. And the encoder's job is done. The encoder can be any deep learning module. Like you might have heard of recurring neural networks or LSTMs, things like that. It can be any of those. And the decoder, the job of the decoder is just taking the latent vector that the encoder has produced and producing the output that we want to have, right? The prediction. And when we are training this whole model, it is trained as a single model by minimizing the distance of the loss between y and y hat. We train the encoder and the decoder. Right? So almost all of the models almost all of the deep learning models falls into this criteria. Some models like NBeats or NHITs, etc., are slightly from a different angle, but most of them, even the transformer models right now, are pretty much this form. So what this lets us do is think about models in different ways and come up with new models as well, right? So suppose you have a RNN as an encoder, as a recurrent neural network as an encoder, and you don't have a decoder, right? You just take the output as is, right? That's basically your vanilla RNN. If you know, one fact is, if you know about what's happening inside an RNN, you know that there is an output gate which takes the hidden state and projects it to the output, or the output that we want. You can kind of look at it as a decoder itself, but since the standard RNN is like a packaged and the output gate is within that, we kind of go with this kind of notation. All right, but then now the output from the RNN, or the hidden states that from the RNN, can also be used in a fully connected network, which is basically your standard feed-forward network, to predict your future. And you can make this like you can predict 1 step or 2 steps ahead or 3 steps ahead. You can like basically design your fully connected network to have n outputs, right? Whatever we need to. That's a very flexible way of doing that. Then we can actually use another RNN as the decoder itself, and this is what is called the sequence to sequence model. So the history sequence is processed by the encoder RNN, you'll get the hidden state, and that hidden state is passed on to the decoder, and the decoder kind of decodes the sequence into how many hour forecasts that you want to generate, right? This is also incidentally the most popular kind of model which was used in NLP. Then we can also use a CNN or a convolutional neural network, like a one-dimensional convolutional neural network, as an encoder, which is basically kind of so a 1D CNN is nothing but a weighted average of a rolling of a window, right? But the weights for that average is learned through training, right? It's very simply, it is that kind of a model, and you can use that to generate multiple features for the latent vector, and then it can use a fully connected network, or we can even use a RNN network to do this, right? So by having this kind of a thought process, you can think about and conceptualize different types of models, and you can even implement it in very easy way, because right now, let's say in PyTorch, RNN, 1D CNN, or fully connected networks are all very, very easy to kind of define, right? So you mix and match. The only limit is your creativity. All right, so with that, I'm going to stop talking about deep learning for a bit, because now we're going to go into something a little more interesting, which is basically called global forecasting models. So global forecasting models are a particular class of models, which I personally I'm really excited about. If I have to bet on one class of models right now to be the best option going forward, I would place my bet on for global forecasting models. And this is a relatively new paradigm for time series forecasting, but not. But this has been known in other words or other terms, something called panel forecasting from econometrics as well. But I think in the past 6 or 7 years, this kind of models have gotten like a rebirth of sorts. And one of the main reasons for that is that so as we moved into this new age, right? We know that our compute cost came down, our storage cost came down, and generally, like we've simply started to store a lot more data. So suppose in the retail context, let's say previously we only used to store like a region level sales, right? Because storage was expensive. But nowadays we store it at the granular level, right? At the store level, even at a half hour interval kind of a level, right? Because it's not costly to do it, and we can just do that. But because of this phenomenon, we have with us a lot of data or a lot of related time series, right? So for example, in the retail domain, you don't just have the history of a single product. We have the history of a lot of related products or other products that the company sells. Even in ride sharing, if you look at Uber, you don't have the demand for one geolocation or a grid. You have the demand history for the ones that are neighboring grids and all the other grids which are there, right? So all of these different time series are now related in one way, and we can see such related time series everywhere nowadays, right? And when we are looking at these related time series, one thing that we can change is that previously we used to think that the data generating process in naive terms is like we assume that there is some hidden process which generates the time series that we observe, right? So there is some process that we don't know, it's generating the time series. So previously we used to think that each time series is going to be generated by another a separate data generating process. But now with these related time series, we can start to think or assume that like all these time series are coming from a single process, right? Just slightly different in some ways, but it has the general properties as same, right? And And global forecasting models is doing exactly that. Uh, in that paradigm, we're considering that the all the time series that are there are coming from a single DGP, and because of that assumption, we can now train a single model to predict or forecast all these time series, right? So if you were using 100 models earlier for 100 time series, we can use a single model for all these 100 time series. So now the natural question that would be there is, why do we want to do this, right? If the other models are working fine, why do we need to do or go with the global forecasting models? So like I said before, right? The last decade, um, machine learning and deep learning have shown that they are performing quite well, and they are what we call data-driven approaches, right? Because we don't have a we don't enforce a lot of structure into these models. We basically leave it to the model to learn from the data, right? And it's partly because of that freedom that the machine learning and deep learning models have done a lot of good things in all the domains. But on the flip side, a data-driven method only starts to perform really well when you have a lot of data, right? And from the time series point of view, getting a lot of data is not really easy, right? Because it's inherently constrained by time. Suppose you have a monthly data set for the last 3 years, right? And you say that, okay, this is not enough. I want more data. What do? You need to wait another year to get another 12 data sets, right? And I'm sure that no business in the world would let you do that, because we want results now. So if increasing the length of the data set is not a really easy thing to do, what we can do is what I call the width of the data set, right? So instead of having a one time series, if we have multiple time series with the same length, we're actually increasing the width. And by doing that process, we are essentially increasing the number of samples that we have in the data set, right? Samples will be the volume of the whole thing. So now suddenly we have enough sample size and to make these data-driven approaches feasible, right? So that's one reason why we want to move to global forecasting models. Another reason is something called cross-learning. So let's take an example from retail again to make it clear. So we all know that ice creams as a product have a very seasonal kind of a demand, right? It has a peak in summer, it has a dip in winter. But suppose if a company is selling lots of different types of ice creams, right? And all of them would have this kind of a pattern, like a peak and a dip, but each of them would be slightly different, right? So in the local forecasting or the previous kind of a paradigm, we would be learning this pattern individually for each time series, independently of each other, right? Maybe again and again learning the same thing. But when we're doing the global forecasting model, we'll be learning the same pattern once by using all this data, so that we have this macro pattern extracted in a more robust manner, right? You can also think about time series with very less length or very less history, right? If you're able to leverage other similar time series in the dataset to help forecast this short history time series, that is also a win for us. So this kind of modeling enables such cross learning and makes the overall output much better. Another reason is that we can think about global forecasting models as kind of like a multitask model, right? Each time series that you're forecasting is another task. So in that task, so when you're doing multitask learning, there are a lot of benefits that come with it, which is one of the main benefits is regularization. To make that clear, probably we can look at, let's say that you have a lot of features and the model is trying to learn, right? when you're doing this multitask setting, the model will be forced to pick a few features which are important for all the time series or a large set of time series, right? So by this way, we are actually not letting the model kind of overfit to one particular pattern or one particular time series, but kind of generalize to a larger set of time series. So that kind of regularization helps the model. And last but not the least, it is the engineering complexity, because gone are the days where we had, say, hundreds of time series to train or to predict, right? Nowadays we talk in millions of time series, which is very real, right? A lot of companies are already doing it at that scale. So when we are training, so imagine that you have 1 million models. You need to train these 1 million models. You need to figure out if it is doing well. You need to serve these models. You need to retrain, monitor. So this becomes an engineering nightmare. But with global forecasting models, you can manage these millions of models, millions of time series with just a handful of global models. Right? And that's a huge win, right? That cannot be understated. The complexity is out of the world. But yeah, so so the global forecast models has been very successful. From my personal experiences, I know that are personally implemented in large forecasting systems for many companies, and almost all the time we end up deploying a global forecasting model um, against all the other competing models, model classes. Um, but even if you don't believe me, because I'm just saying, but even if you look at the public domain, right? If you look at the last few years of forecasting competitions, all the way back till 2015 in the Rosman store sales itself, a global machine learning model was the winning model. And even if you look at all the other competitions which happened, one which are as recently as M5 forecasting, M6 is done. I'm not sure if the results are released yet, but even the M5 forecasting, everything was either a global forecasting model, global machine learning, or deep learning, or an ensemble of different models. Right? So this particular class of models have become like the go-to model for the industry lately. And that's also one of the reasons why one of the main motivations behind me writing that book as well is that when I was going through the journey of implementing these large scale forecasting systems, uh, when I looked for guidance or when I looked for other resources online, I didn't find much resources there. All the literature basically talks about time series and talk about IDMA and exponential smoothing, and then they stop there. But when I was looking at the industry and how things are done there, there is a huge difference, a huge gap. So that's basically why the whole motivation behind writing the book. But yeah, I sidetracked. Let me come back. So now that I hope, hopefully I have convinced and motivated you about global machine learning models, let's look at how we make a global machine learning model, right? Let's say that you have two time series, right? Time series 1 and time series 2. We already know how to convert them into a regression kind of a form, right? So we do that. So now, when I tell you how we're going to do this, you're going to laugh at me. But all we're going to do is take these two data frames, combine it together into a single data frame, and train one single model on it. Right? Technically, this is still a global machine learning model, although it might not do that well because we need to do some more feature engineering to get this thing working better. Which is what we are going to look at in the next couple of slides. Right? So how do we get these things better? The first thing is increasing memory. Instead of just 3, we can have more lags. And these are all the features that we already talked about, right? So adding more memory is in the window that you give, or the window of information that you give to the model. So so there's been studies by, there's a paper from Montero Manso, I might be butchering the name, but Montero Manso and Rob Rob Hillman, who's, everybody knows Rob Hillman. So they have kind of taken, it's not a paper, it's an understatement to call it a paper. It's a book, basically. It's like a 30, 40 or more pages of paper. So they've done really extensive studies on this global forecasting models. They've analyzed theoretically and empirically on what makes these better, right? So that kind of resonated with the learnings that I got from my personal practical approaches as well. So like that paper is a must read. But yeah, so they've shown in the paper theoretically that increasing the memory gets better performance up to a level, and they've showed that empirically as well in that. So adding more memory is definitely one way of doing it. Then another thing is we can include meta features, right? So by meta features, what I mean is, so right now we're trying to train a single model to predict multiple time series, right? So as things stand now, it just have lags and some historical memory. It doesn't have any information with which it can differentiate these different time series from each other, right? So some time series might have a different pattern than the others. So that information is what we are trying to inject through these meta features. So it can be, let's say that we can get some time series characteristics, right? Statistics, mean, median, kurtosis, different statistics that you can take from the time series. You can include that as a feature, in the model, or you can start to include hierarchical features, basically categorical features. For example, in retail, you have these product hierarchy. Right? You can include them as features, or you can have some location aspects as features. And in our example, I earlier talked about, there is something called the Acorn, basically like a household categorization. That's also a feature that you can add. Right? All these things are unique to a time series, and this helps the model kind of segregate the space in a better way so that it can learn separate patterns for different types of series. But then when we are including these hierarchical features, most of them are categorical in nature. And what happens here is that the most straightforward way of including a categorical variable in the machine learning model is one-hot encoding, right, or dummy encoding. But that's something that is not really scalable. Like if you have a lot of unique values, or the cardinality is quite high, that kind of increases the feature space by a large margin, and it becomes detrimental. Again, the curse of the dimensionality space. So there are other ways of doing categorical encoding. Some things like target mean encoding or frequency encoding. There are different ways of doing it, which still makes the encoding into a numerical feature, but does not have the disadvantage of adding like 1,000 feature to it. Right? Yeah, in the book, I'm going into a little more details and talking about what are the different methods and how we can use it, etc. But then, yeah, that's another thing that you need to keep in mind. Another way of getting these models to do better is by doing partitioning. This is slightly counterintuitive because on one side, I'm saying that by having larger sample size and larger data, you're getting better models. You're able to better train a data-driven model. But partitioning means splitting the whole data set into smaller parts is also a good way of increasing performance. So the same paper that I mentioned earlier, they've shown theoretically that partitioning it makes the model learn better. There's always a sweet spot, right? So you can partition. So if there are n time series in the data set, and if you do n times n partitions, which means that you're basically at the local modeling paradigm. And if you do one partition, it means it's the global model, right? So there is a sweet spot in between, which will give you the best possible performance. Right? But from the intuitive way as well, if you think about it, Let's say that you have a data set which has ice creams and let's say rice or some staple good, right? These two have very different patterns, right? So now when we are modeling it together, the model has to work that much harder to learn both of these patterns and have a decision pathway to kind of say that if this is the category, then we should have this pattern, and that otherwise that pattern, etc. Right? But instead of that, if we just have two different models, one for the staple good and the other for ice cream, it makes the model's job much easier. So that's what we are talking about as well. There are different ways of doing partitioning. The most counterintuitive way is random partitioning, but the paper that I mentioned, they showed even experimentally that even doing a random partition has some gains. But typically in the industry, we end up doing judgmental partitioning. We'll use some attribute of the time series to kind of group them into logical sections and train different models on it. But if you don't have such an intuition, you can always go with algorithmic partitioning as well. You can use clustering algorithms to cluster different time series and then have different models trained on each of these clusters. And last but not the least, we have hyperparameter tuning. Right? So this is typically important for global machine learning models because in the local way, right, if you have like 1,000 or 2,000 or 5,000 different models, doing the hyperparameter tuning for each of these things are not really simple. Right? It's going to be really computationally taxing to do it. And you might not get good results. But when you're doing global models, when you have a handful of models, hyperparameter tuning is your friend. So there are different ways of doing hyperparameter tuning. Each of them have its own pluses and negatives, right? One is grid search. So grid search is basically a brute force method. It exhaustively searches a search space that you define and is guaranteed to find the minimum in that search space. But the caveat there is that you'll not be able to define a large enough sample space or a search space to get good performance because it is simply computationally expensive. Right? It'll take for a long time to run the grid search on that. On the other end of the spectrum, you have random search, where you can define as large a search space as you want. But basically, you pick random points in the search space and keep evaluating them and pick the one that works best. So this is also, it's kind of like throwing a dart with your eyes closed and trying to hit the best point or the middle point. And somewhere in between comes Bayesian optimization, which is similar to random search. But so while random search, it starts off as a random search, the Bayesian optimization. But unlike random search, after each trial or each, let's say in the example that I talked about, the blind dart throw, after each dart throw, you're able to look at the results of all of your previous dart throws and see that, okay, this is an area where I'm getting more score. So then I can choose to focus my efforts on that area more, or that search space, that space in the search space more than the others. But then occasionally I do some exploration of the other areas to see if I'm not missed or I'm not stuck in a local minimum or something like that. So by this exploration and exploitation, Bayesian optimization converges to the minima much faster than random search, and you're able to search a larger search space than grid search. So Bayesian optimization is a very good way of handling this. Out of these three, I would personally prefer to do Bayesian optimization. All right. So just one more thing before we break, right? So this is the global machine learning. We were talking about global machine learning models. So what about deep learning models, right? So all the deep learning models that you hear about today are almost exclusively trained in a global way, right? it is trained on multiple data sets together, right? By using some techniques that we've talked about earlier, or something that I'm talking about now. We'll talk about now, right? So in any forecasting or in a deep learning system, whether it is based on PyTorch or whether it is based on TensorFlow or any other system, you would have to create some batches of data, right? And for that, you will typically need data loaders or something like that, right? Which takes your data and forms it into a particular way. But one thing that we need to keep in mind is that there are different types of variables that we are going to use in a system, right? There are static variables, right? By static variables, what I mean is all the meta features that we talked about, right? It doesn't change with time. It is a single value for the entire time series. And then there are time varying features, which basically varies with time, right? For the time varying features, it is also essential that we know the future, right? There are also ways of modeling time varying features without the future. Let's keep that out for now. Let's say that time varying, we need a future as well, so that you using that as a feature for the future thing as well. And then these variables can be categorical or it can be real numbers, right? So depending on these different classifications of features, the way you handle that in a model slightly differs, right? So so suppose I'm just taking PyTorch forecasting as an example, and this is incidentally the same package that I'm using in the book as well. But it is not the only one. There are other equally good or slightly better things in the market as well. But yeah, for PyTorch forecasting, what it does is it lets us kind of define. Like all we need to do is we have a data frame. We just define that this is my target. These are my time varying unknown. These are my static variables, if any, etc., etc. We just define my features. I also define a normalizer. I'll talk about it in just a minute. Once you do that, the rest of the whole thing, this package handles, right? It gives you the encoder part and the decoder part separately. So encoder is your history, and decoder is the horizon that you were trying to forecast. And it also separates your categorical and continuous variable, because the way you handle categorical variables is slightly different than continuous. Because at the end of the day, all of deep learning boils down to matrix multiplications, and you can't do matrix multiplications with strings. So you need to convert that into a numeric form. So I'll talk about it in a bit. So, and another thing that we typically use, especially in the global, especially in the deep learning framework, is something called normalizers, which is essentially saying that we're trying to, like, there'll be different time series in the data set, right? So some time series might be in thousands, that the values might be in 1,000, 2,000, etc. And some things might be in 1, 2, 3, etc. Right? Since we are learning a single model for all of this, we are actually giving the model an additional task to learn or generate these different scales of numbers as well, right? But then if we just take everything down into a fixed scale, let's say between 0 and 1, that makes the job of the model a lot easier, right? So the group normalizer basically just does that in a particular way. So this is how we get the data loaders, and then we define the models, etc. I'm not going into the definition of the models because it is too much for a session. But this is I'm just telling you this to understand that there are like packages. First of all, there are packages like PyTorch forecasting, so things like Gluon TS, PyTorch TS, Neural Forecast. A lot of the packages are there. Almost everyone follows this sort of distinction. You have static, real, static, categorical, time varying, and time varying, right? So that thing is there. So getting a model up and running is pretty easy. Getting a good model is a difficult task. Getting a model up and running is easy enough nowadays. You can just use these packages to get that going. Right. Now let's also look at a few things where we typically use in deep learning to get these models better. So yeah. So yeah, the first one is something called entity embeddings. So this is basically, like I told, we talked about earlier, right? The categorical features need to be treated in a slightly different way. So entity embeddings are a way of doing that. So we basically taking a categorical value and projecting it into a dense vector or real vector. And how this projection is done is actually learned along with the model, right? So it's very similar to the word vectors, word to vec that you must have heard from NLP side. So you have a particular word, you have a corresponding representation on the other side. This is very similar. So the good thing about this is you don't need to define how to represent the categorical feature. It is learned along with the task, right? And even after training, you can actually use these embeddings to analyze your data. Like for example, you've done the entity embedding for month as a feature, right? After the model is trained, you can just analyze them to understand what months are more similar to each other, etc. Right? And the next one is the scale of the series. So earlier we talked about normalizing the target, right, for computational efficiency, right? But there is a flip side or a downside for it, because sometimes the scale of the model or scale of the time series is also a good information, right? Like high valued time series may have slightly different pattern than a low value time series. So by adding the scale of the series as a feature, right, we are actually adding back the information that we've removed by normalizing. And that most of the cases helps in modeling. And the last one is around balance sampling, right? So in deep learning, how we train a model is not by using the entire data set in one stretch. We take batches of the data and we train the model on that batch. And then we cycle over the entire data set. Right? So what happens is that suppose you have a few time series which are large, or you have a lot of data or a lot of history, and few time series which are small. So if you just look at the proportion of these time series, right? These large time series would have a large representation in the sample space, and small ones would not have much. But if our intention is to learn both of these patterns equally, let it do something special. Because in the standard batching, whatever imbalance that you see in the data is going to be there in the batch as well. So what we end up doing is that we learn patterns which are on patterns better, which is on the large time series, and we'll ignore the smaller ones. So we can do some kind of balancing while we make the batch, such a way that each batch is a balanced representation, so that the learning happens equally on different types of different patterns of time series, right? So yeah, with this so this is how we kind of also improve global machine learning or deep learning models. Okay. All right.